All right, and we are back again with the interesting stuff. So the B lecture for week 5, in which we'll take a further look into mediation and interaction effects. So as always, I'll start with a recap on moderation and mediation. So what do we know now? And then we'll take it a step further in looking at how we can interpret these interaction effects in a way that is a bit more intuitive and more meaningful than we have done so far. And then I'll talk a little bit about mediation and a new concept, suppression, and an old concept, spuriousness. And I'll talk a little bit about what the difference between these three concepts is, because they look very similar if you think about them in terms of how variables are related to each other. So I think that's important, and we're now at the point of the course where we can have a meaningful discussion about that. But let's start with a recap. What do we know now? Well, we know what moderation effects are, what moderation hypotheses are. We know that they are sometimes referred to as interaction hypotheses or interaction effects because, moderation, because there is a variable that moderates the relationship between another variable and the independent variable. So there is a moderator variable x2 in this picture that moderates the effect of x1 on y. So that changes what the effect actually is. So that's why it's called moderation, and it's sometimes referred to as interaction because x1 and x2 are interacting with each other, in that effect on the dependent variable y. So that's one thing that can be theoretically super interesting because it allows you to analyze the conditionality of your effects, and that is often super interesting because it tells you something not just about does the causal mechanism that we want to test work, but also under which conditions does it work, and in which situations, for which cases does it work stronger or weaker or not at all. So that's super interesting. So this x2 variable then would be called the moderator, and the x1 variable would just be our independent variable. But we already saw that if you do that statistically in a model, then which one of the two variables, x1 or x2, is the moderator and which one is the independent variable really depends on your theory. So which one can theoretically be considered to be the moderator and which theoretically can be considered to be the independent variable, because mathematically it doesn't matter. We still get the same coefficient for our interaction term. Another thing that we saw in at the beginning of this week is that we can also do another type of analysis, so-called mediation analysis, where we're looking at how the effect of some independent variable x on a dependent variable y can be unpacked into an indirect effect and a direct effect. And we usually do that because theoretically we have some argument that tells us why it is that x leads to y, and that argument, that causal mechanism, involves a z variable, a third variable z that we can actually measure. And if that's the case, then we can do a mediation analysis to see, is that really true? Is that really how it works? So we can go a little bit further in testing our causal mechanisms by seeing, what is then the indirect effect of x on y that runs through that z variable, that mediation variable, and what is the remaining direct effect, if there is any remaining direct effect of x on y, so that we can basically unpack this total relationship between x and y into an indirect and a direct effect. Again, because causal mechanisms imply that there are steps in between, and sometimes we can actually observe the steps in between, so that gives us more room to test our theories. So then that third variable, that z variable, is called a mediator variable. So we looked at both of these things. So we know mediation is basically unpacking the total effect of x and y into an indirect effect, from x to z and from z to y, and a direct effect. So that's the effect of x and y that remains once we take into account differences on the mediator variable. Right, so one thing I want to now discuss is how to help yourself, and if you're reporting your research findings, how to help others in interpreting interaction effects. Because so far we have basically just talked about, the interaction effect itself tells you something about how much the slope of the regression line for your independent variable changes when the moderator variable increases by 1 unit of its scale, which is completely correct, and it's certainly helpful. But of course, it's only part of the story, because this, for instance, doesn't tell you, well, okay, from where to where does that regression line actually change? Yeah, is it from a very negative effect, for instance, to a somewhat less negative effect, or from a positive effect to a super positive effect? You can't tell from just looking at the interaction coefficient itself, because it only tells you how the regression line changes, not from where to where does it actually change. Yeah, so for instance, a positive interaction coefficient of 0.5 could be reflecting a super negative effect on your independent variable that becomes less negative by 0.5 points on the slope coefficient for every 1 unit increase in your moderator, but it could also indicate a already positive effect on your independent variable that increases further by with a slope with an addition to the slope of 0.5 for every 1 unit increase in your moderator variable. So of course you would want to know, well, exactly what does the interaction effect actually look like? So not just how it changed, but what does the overall effect actually look like? So we are going to analyze this a bit further, and I'm bringing back the SPSS output that I already showed you in the example from what is here listed as Monday, but which was of course the A lecture for this week, which you may or may have not watched on Monday. Hooray for asynchronous classes. Yeah, but this was what I already showed you in that lecture. So I estimated this interaction model where I checked the interaction effect of age with religiosity, and I used income as a control variable. So let's now take a further look as to how to interpret these results. Well, first off, what I would always recommend doing if you want to interpret regression models, well, write them down first, preferably with pen and paper, but I'm going to do this on the slide here. So I'm just going to write out, okay, what does this model tell me about the predicted value for satisfaction with the national government? So the predicted value on our y variable, so the y hat value. Well, it tells me what the constant is, and that is estimated to be 4.002. Yeah, so in other words, that's a predicted value of if all the other variables in the model are at their 0 value. It tells me that I have to subtract from that constant 0.003 multiplied by the value of age for each respondent, but we didn't use the original age variable, we used the age-centered variable, so that this main effect is more easily interpreted as being the effect of age for people that are averagely religious, and vice versa then for the religiosity effect that we can interpret as the effect of religiosity for people that are of average age. Yeah, so but this is writing out the model. We get a constant of 5.02 minus 0.003 multiplied by age-centered for each respondent plus 0.042 times religiosity-centered, so the main effect for religiosity, plus the income effect, which we used as a control variable, income in this case, so that's plus another 0.174 multiplied by the value of income for each respondent, plus 0.002 multiplied by age-centered and multiplied by religiosity-centered, because that's our interaction effect, that's our interaction term. How did we create that interaction term? We multiplied the value of age-centered with the value of religiosity-centered for each respondent, and then included that as an additional variable in our regression model. Yeah, so this tells us now what the model actually looks like if we write it out. If we really want to understand what is happening here, one thing we can do is what is sometimes referred to as a simple slopes analysis. And it's called a slopes analysis because what we're going to do is we're going to literally look at how does the slope of our regression model for the effect that we're interested in, how does that slope change? And it's called simple because there are also more elaborate and more complicated versions of doing that. But this is definitely a nice start to get a handle on interaction effects for a second-year statistics course. So a simple slopes analysis. So what is the idea? The idea is that if we really want to understand how the interaction effect works, so what it actually looks like, we are going to just calculate the slope of that effect for our independent variable at different values for our moderator variable. So we're going to calculate for different values of our moderator variable. We're going to see, well, what is the actual effect like of our independent variable? What kind of slope do we find for that independent variable? And the values we usually choose are low, average, and high values. Yeah, so that you have an idea of what does the effect look like if the moderator takes a very low value. What does the effect look like if the moderator takes an average value? And what does the effect look like if the moderator takes a high value? It's just arbitrary, basically, how many of those values you pick and exactly what values you pick. So we are going to use this very standard way of doing that. So we're going to pick 3, low, average, and high. And what we take as average, we are going to literally take the average, so the mean value. Yeah, so we're going to pick the mean value of our independent variable, of our moderator variable as one point at which we are going to evaluate the effect of our independent variable or dependent variable. And we are going to use as a low value, we are going to use the mean value on the moderator minus 1 standard deviation on that moderator variable. Why minus 1 standard deviation? Well, the idea is that what is a good representation of a low value? Well, we could have all kinds of different low values, of course, but the very extreme low values are maybe not so super informative because those tend to be very, very few numbers of cases that have the very extreme, the absolutely lowest values that you observe overall. So instead of that, we pick something that is low, but is still relatively common. So then the mean minus 1 standard deviation, that's a nice way of picking a low value that's definitely low relative to the mean, but at the same time not super rare either. So that's just one way of doing that we are going to use here. So for a low value on the moderator, we're going to pick the average on the moderator, the mean value on the moderator, minus 1 standard deviation, and then for the high value, reversely, we're going to pick the mean value plus 1 standard deviation. Yeah, so again, the idea is that we don't necessarily want to use the highest observed values at all on the moderator variable because there probably won't be so many of those. So we want to pick a point that's high relatively, but not so high that it's just reflecting the effect for very rare numbers of cases. So again there, the average plus 1 standard deviation makes a lot of sense as a high value. Yeah, so from the example that I showed you, we used age-centered, that was our moderator variable, and I have looked at what is the standard deviation of age-centered because of course I need that to add to the average if I want to calculate the high value and subtract it from the average if I want to calculate the low value. Yeah, and the average itself the original, if you're talking about the original variable of the moderator, then the average corresponds to the 0 value on the mean-centered version of the moderator. So as the average, we just pick the value 0 on our age-centered variable. This is a matter of fact, this is exactly the reason why we did this mean centering, because then we just shifted over the 0 on the new variable to where the mean value of the original variable was. So now the 0 value on age-centered corresponds to the mean value on the original age variable. So it is really an average value on age that we are capturing with this mean value. And then a low value is just this 0 minus 17.26. So the mean minus 1 standard deviation. So that works out to a value of minus 17.26. And the high value works out to 0 plus 17.26. In other words, just 17.26. Yeah, so if we are doing this mean centering trick, then all we need to do is look up the standard deviation for our moderator variable, and then we're going to pick as a low value minus the standard deviation. As an average value, we're just going to pick 0 because we mean-centered, and as a high value, we're going to pick just the standard deviation, so the positive standard deviation. So that's quite useful. So now we know what values we want to plug in to our moderator as a value for the moderator variable and evaluate the effect of our independent variable at. Yeah, so minus 17.26, 0, and positive 17.26. So how do we do that? Well, we just fill in the formula. So this is the formula that we had. Yeah, so we have a predicted value for a dependent variable equals a constant plus a main effect for age-centered plus a main effect for religiosity-centered plus an interaction effect. What I did in this model, and this is just because I ran out of room on the slides, I took out the income variable just to make it a bit simpler and keep a bit of the overview on the slides. And the nice thing is it doesn't really matter for what we are about to do. All that differences in income then do would be to lead to a further overall increase or decrease on the predicted value of the dependent variable depending on different values in income, but it doesn't matter for the evaluation of the interaction effect actually in the way that we are doing it here. So we can just forget about this income variable for now and just take a look at just the main effects for age and religiosity centered and the interaction term. Yeah, so that is just to make things a bit simpler. So we know low values, high values, and average values for our moderator variable. So the low value we picked is the value where age-centered corresponds to minus 17.26. So basically, this signifies the people that are that are 1 standard deviation below the mean age. So these are the super young people. Yeah, so we can just plug in that value into our formula. So wherever it says age-centered, we are now going to plug in the value of minus 17.26. Yeah, so we had age-centered as a main effect here, and we had age-centered in the interaction term here. So we're going to plug in this minus 17.26 for the main effect over here, and we're going to plug it in the interaction effect over here. And then all we need to do is, well, work out what does our model say if we work this out mathematically. So we can just do this in a couple of steps. So the first thing I did here, as I said, well, I can take this, I can work this out mathematically. So minus 0.003 times minus 17.26. What does that work out to? Well, minus times minus is going to be plus. It's going to be a positive number. And the number that I found on my trusty old calculator is 0.05178. Of course, check for yourself. I hope that you have your old trusty calculator next to you or your smartphone. But make sure that it's correct and that you can follow along. Yeah, so this is the first thing I simplified. I just solved this part of the formula, minus 0.003 multiplied by minus 17.26. Everything else is still the same. I just simplified that part of the formula. So I can also do this for this part of the formula for the interaction term, because also there we plugged in minus 17.26. So now I know that the interaction term was 0.002 times minus 17.26 times religiosity centered. So I can multiply these two numbers with each other. So 0.002 multiplied by minus 17.26 works out to minus 0.0342. Yeah, positive times negative is a negative number, and this is the number that I found, minus 0.0352. Again, of course, check for yourself so that you know what is going on. Yeah, so now we have further simplified this model. It's still the same model, we are just simplifying by solving what we can solve here mathematically already. Yeah, now there is one trick that might be a bit surprising to you, but because we have religiosity centered now twice in the model, so now basically we have the model, we have simplified, and we have here an effect for religiosity centered. This was our original main effect, for which we have a coefficient then of 0.042, but now we have a second effect just for religiosity, which works out to minus 0.0352. So it's basically now all of a sudden we have two religiosity effects because we took out basically, we pinned down what the value for age-centered is. So what we are left with is two effects that are about the same variable. Both of these effects, both of these coefficients are about the religiosity-centered variable. Now, whenever you have two coefficients that are about the exact same variable, you can just add them up. Yeah, so you mathematically you can just add up the values of those two coefficients to reduce that to a single effect, because it's both of these coefficients are about the same variable. So we can just add up this plus this 0.042 and add up to that the minus 0.0352, which of course works out then ultimately to 0.00748 because it's basically 0.042 minus 0.0352, yeah, plus minus equals minus. So now we have further simplified the model. So now we have 4.02, the constant, plus 0.05178 plus 0.00748 times religiosity centered. Yeah, so all of this is just the same model with plugging in minus 17.26 for H-centered. It's just that we are simplifying it mathematically, but it's still the same model. So what does it tell us now? Well, we now have one effect for religiosity centered, and that effect is 0.00748. So what does it tell us? It tells us that at age values that are 1 standard deviation below the mean age, so for really young people, so for people that are 1 standard deviation below average age, the slope of the religiosity effect is equal to 0.00748. So now we know what the effect of our independent variable and our dependent variable, what that looks like for people that are really young. So for people that score a low value on the moderator variable age, right? Then that is 0.0748. So if we would visualize that, what would the effect look like? Well, we can take, we're going to put the religiosity on our x-axis because that's our independent variable. And we have our predicted value on the dependent variable on the y-axis. So in this case, it was satisfaction with government, I think. Yeah, so now we can try to visualize, well, what would that look like? Well, it's a positive coefficient. So it's an upward sloping regression line. And the value of that line is 0.0. The value of the coefficient that describes that regression line is 0.0748. Yeah, so this is now the slope for the religiosity effect for people that are 1 standard deviation below the mean age, for the really young people. Yeah, this is what we now have learned. We have also seen that what the constant is for these people, because we saw that we were left also in our regression formula with 4.02 plus another constant value of 0.05178. Yeah, because we solved the main effect for age by plugging in minus the standard deviation. Yeah, so we now also know what the constant is, so the intercept is for this regression model for people that are 1 standard deviation below the average age, and it's a little bit above 4.02. So it's 4.02 plus 0.05178. Yeah, that is the constant of this regression equation. Yeah, so this is what the effect looks like of religiosity on the predicted value of our dependent variable for young people. Of course, we can also do this for average aged people, so people for which the age-centered variable takes the value 0. Yeah, so then we know what the effect looks like for people with an average with the mean value on age. And again, the trick is, well, just fill in the formula. We have this overall regression formula, and wherever we have age-centered, we're going to plug in the value for age-centered that at which we want to evaluate the religiosity effect, which is now the 0 value. So this minus 0.003 gets multiplied by 0, and also in the interaction term we had age-centered, so also here we multiply the interaction coefficient of 0.002 by 0, and then that is multiplied still by religiosity-centered. Yeah, so now we just plugged in the value 0 wherever we had age-centered in our model, and again we can just mathematically work out this model and simplify it step by step. So 0 times minus 0.003 equals 0, because whenever you multiply something with 0, you get 0, right? And if you get 0, you can basically forget about it. It doesn't add anything to the equation anymore, and you can drop it from the equation. Yeah, so now we know that we get a 0 for what the main effect of age-centered. Of course, we can also do this here. Multiply the interaction coefficient with the value for age-centered that we now picked, which is 0. Again, if you multiply something by 0, the result is always 0. So now we know that we are left with here with 0 times religiosity-centered for that interaction term. And then we can say, well, that means that we can basically forget about this interaction term, because that means whatever value on religiosity-centered people score, it will be multiplied by 0. So it works out to a value of 0. So we can just drop that from our equation, because it doesn't add anything anymore to the equation. And of course, we can also drop the 0 that we had here already, because again, it doesn't add anything to our equation because it's just a 0. So for age-centered, we are left with a religiosity effect that's described by a slope coefficient of 0.042 and a constant of 4.02. Yeah. So in other words, we now know that for people with an average age, so for people for which age is at its mean value, again, because those are the people for which age-centered takes the value 0, for those the slope coefficient of the religiosity effect is 0.042. Now, that was nice, that was mathematically certainly very interesting. We didn't actually need to do this, because this was exactly the effect that we got for the main effect for religiosity in the SPSS output. As a matter of fact, that's exactly why mean centering works in making the main effects easier to interpret, because again, if what is the main effect in an interaction model? It's the effect of that variable if the other variable is at the level 0, and by picking the mean values, by mean centering the moderator variable, we have basically made sure that the main effect is now the effect of religiosity for people of an average age. So we didn't actually need to do all this stuff. We could have just looked at the SPSS output and we would have seen, yes, that it is indeed 0.042. Yeah, so, but again, it's good to know why that is actually the case, and probably you were still maybe a bit uncertain about why does that whole mean centering work, and why does it mean that we can now interpret the main effects as the effects of that variable is if the other variable is at its mean value. Well, hopefully now you understand a little bit better. So this is certainly quite helpful, because it means we can just look at our regression table if we want to know what the effect is of our independent variable. If the moderator is at the mean value, is of course super useful, because the mean value is going to usually be the a value that quite well describes the center of the distribution of our moderating variable. So where the most cases are basically located around. Yeah, so that's useful, of course. Yeah, so now we can add to this visualization of the effect. We already had this. We already had, with the green line, the effect of religiosity for people that are super young, so people that are 1 standard deviation below the mean age. So we already knew what that looked like. Now we can just add what we now saw is the effect of religiosity for people with the mean age, so people of an average age, which works out to a slope coefficient of 0.042. Yeah, so now we see how this interaction actually changed the slope coefficient for religiosity. We see that for people with a mean age, the effect of religiosity is stronger, more positive in this case, than for young people, so that are 1 standard deviation below the mean age. So now that's already a lot more interesting, right? Because now exactly we know what the effect is for people with a mean age, and we know how much less steep, so less positive it is for young people. And we also see that the intercept in that regression model is going to be lower, so for people that are at the mean age, because remember, for people that are super young, so that are 1 standard deviation below the mean age, we found that the constant was 4.02 plus 0.05178, and now we have seen that for people that have a mean age, so that are of average age, that the constant is just the original value of 4.02. So that's a little bit lower, of course, than 4.02 plus 0.05178. So we see that the slope increased. Yeah, so we have a stronger effect for older people, for people of the mean age, than for the young people. But we also saw that the constant went down. Yeah, so that the predicted value on our dependent variable, if religiosity is at 0 value, is actually lower for these somewhat older people than for the young people. Yeah, so that's a visualization of what we know now. Of course, we can also do this for old people. So we're picking a high value on the moderator variable. So we picked the standard deviation, so the average age plus 1 standard deviation, which works out to plug in 17.26, the value of the standard deviation for age-centered. Yeah, so every place in the model where we have age-centered, we are now going to plug in the value 17.26 and again work out the formula. So plugging this in, again, I get minus 0.03 multiplied by 17.26, because there we had age-centered, and I get 0.002 multiplied by 17.26 because there we had age-centered multiplied by religiosity-centered. So for the main effect of age and for the interaction term, we can plug in 17.26 and then we can again work this out mathematically. So again, I'm first solving the main effect, so minus 0.003 multiplied by 17.26 works out to minus 0.05178. Again, minus negative plus multiplied by positive gives you a negative result. And again, check with your calculator, of course, if this is actually correct. Yeah, so that's one step in which I can simplify this model. And I can also do that here by working out this part of the formula. So 0.002 multiplied by 17.26 works out to 0.03452, and then still religiosity centered, of course, which we have in that interaction term. So now we multiplied this by this, and now again we have a situation where we have two effects for religiosity centered that are still in the model. So the original main effect that we had of 0.042, plus now the interaction term that we had, but because we plugged in a fixed value for age centered, all that we have left is another effect for religiosity, which is 0.03452. So again, if you have two coefficients for the same x variable in your model, so it's in there twice and nothing else is multiplied with that variable, you can just add up those two coefficients to make a single new coefficient for that variable, because mathematically that's exactly identical. So we can just add up the 0.042 from the main effect with the 0.03452 for the interaction term, and just add those two values together for one coefficient for the religiosity centered effect. So that works out to 0.07652 for the effect of religiosity. So now we have worked out the formula to be for the predicted value of a dependent variable that is equal to the constant that we started out with of 4.02 minus now another constant value of 0.05178 plus the coefficient for the effect of religiosity, which is 0.07652. So in other words, at age values that are one standard deviation above the mean age, so basically for old people, the slope of the religiosity effect that we estimate is 0.0652. Right, so now we know what the effect is of religiosity for the older people. Again, we already had this visualization, so we already knew what the slope was for the young people. We already knew what the slope was for the people of average age, and now we can just further add to the visualization. Well, what does the slope look like for old people? Well, it is again a larger number that we found. Yeah, because we had a positive interaction effect, so we know that the slope is going to increase. And now it increased to a value of 0.07652. So we have a much steeper regression line for people that are one standard deviation above the mean age. Yeah, and again, we saw that we are left with a constant value for the main effect of age, and that turned out to be a negative number, so minus 0.05178. So that means that the constant for people that are one standard deviation below the mean age is actually lower than 4.02. So it's 4.02 minus 0.05178. Yeah, so now we see exactly what our interaction effect looks like if we consider a, let's say, an interesting range across our moderator variable. So we know what the effect is like for young people, for medium-aged people, and for old people. We know exactly how the slope changes, and we also know how the constant changes. And it's actually important that we allow that constant to change, because if we wouldn't do that, if we would assume that the constant is the same for everybody, well, in reality it isn't, then we would force to all these different regression lines to all meet exactly at the same point on the y-axis, which of course often is not going to be the case in practice. So what would happen then is that you would get a huge bias in your interaction effects, because basically you would be forcing all those regression lines to meet at the same point. Yeah, so if you consider this example, you would probably you would need to push this line downwards and this line upwards to make sure that they meet at the same point, which would make those lines much steeper, so the red line much steeper and the green line much less steep than it is in reality. Yeah, so you always want to allow there to be a different constant also for the different for the different values of your moderator variable, which is exactly what we do by including the main effects of the moderator variable. Yeah, and this is also the reason why you should never only include an interaction term into your model, but also you always include the main effects as well, because by including those main effects, you are allowing the constant to be different for different values of your moderator, which if you're doing social science type research, it's never a good idea to not allow that, because you will really run the risk of having hugely biased results. Yeah, so that's the reason why we always include those main effects as well. So this is a little bit like when we discussed the polynomial effects, where I said you always have to include all the lower order terms, because otherwise you can get quite a bit of bias. It's the same thing for interaction models also there, because you're making more complicated terms now. So higher order terms, basically, again, always include all the lower order terms as well, or you will get really nasty bias and really misleading results. Yeah, but that's it for interpreting this interaction effects. I'll probably put a link on Brightspace to a website where there is some nice Excel sheets that allow you to make these kinds of graphs yourselves for your own research papers. So that might be interesting for you, especially if you, let's say, want to do some interaction analysis for your comparative governance paper, or for your thesis later, or for other research that you're doing. Then that helps you with making these visualizations of the effects. Yeah, so that's about interaction effects. Now let's talk a little bit more about the conceptual issue that I think now is the time to address. Now let's talk about mediation and how that differs from something called suppression and something else we already discussed, the idea of that there are spurious relationships. So mediation, we saw where we can think about mediation as we start out with some simple relationship between an independent variable and a dependent variable. Yeah, so given by this top part of the graph that I have here, and we can disentangle how that relationship comes about by disentangling that into an indirect effect through some mediator variable and the remaining direct effect from the x variable on our dependent variable y. Okay, so one thing to discuss here is that we can distinguish between two situations. A situation where we say there is full mediation and a situation where we say there is partial mediation. So what do we mean by that? Well, the idea is that if we talk about full mediation, then what we are talking about is a situation where the original effect of x on y is entirely explained by this indirect effect through the mediator. Yeah, when you say that the effect that we started out with, that is entirely due to the mediating variable. So in that case, one way of assessing whether that's the case, whether you have full mediation, is by looking at the statistical significance of the C apostrophe part, so the direct effect that remains once you adjusted or controlled for differences in the mediator. Because if you can, well, if that's very close to zero, and maybe if it's also not statistically significant anymore, then you might say, well, that suggests that there is actually full mediation, that the entire original relationship is being captured by this indirect path, and there is no remaining direct effect left anymore. Of course, that's a bit difficult as to how strong is the evidence if it's not significant anymore, because just because it's not significant doesn't mean that there is no remaining direct effect in the population. Yeah, so a low p-value, a high p-value only means that you can't reject the null hypothesis. It doesn't mean that the null hypothesis is true. But it's at least a piece of evidence that you can use to assess whether there may be full mediation, which is actually quite rare in the kind of observational data that we usually analyze. What we much more often have is a situation of partial mediation, where you say, well, there is part of that original relationship between x and y that I can really say, well, this is really due to this indirect path through the mediator variable, but I still have some direct effect that is left, and that might still be, for instance, if that's still statistically significant, that's a piece of evidence you can use to say, well, there is evidence of partial mediation. So yes, all the 4 conditions are supported by our data that we discussed. Yes, so the C apostrophe effect is smaller than the original C effect, but it's still a significant, statistically significant effect. And you can say, well, it suggests more that it's probably just partial mediation that we are looking at here. Yeah, so this is just to get the terminology on that straight, so you realize what people talk about when they talk about full mediation or partial mediation. Now, one thing that we also should consider, because I used a simple example where there was a positive mediation effect, but of course it could also be the case that you want to look at the mediation effect for in a situation where X has a negative effect on your dependent variable, so there's actually a negative relation, a simple relationship. And that's of course also completely possible. What you just should realize, that implies that your indirect effect has to be negative. And given that the indirect effect can be calculated as A times B, so the coefficient from X to Z multiplied by the coefficient from Z to Y, that means that either this coefficient that you find for A or this coefficient that you find for B has to be negative. But they can't be both negative, right? Because you can only get a negative effect, so A times B can only give you a negative result if either A is negative and B is positive, because negative times positive gives you negative, or if A is positive but B is negative, because positive times negative gives you negative, but they can't both be negative because negative times negative again is positive. Yeah, so you can think about that as intuitively that what does that mean? It means that if we expect a negative indirect effect, what does it mean? It means that 2 situations could be the case, that your independent variable pushes up the values on your mediator variable, so makes the mediator variable take higher values, but the mediator variable itself pushes down the value of your dependent variable, right? So that means that you have a positive A path and a negative B path. So higher values on the independent variable lead to higher values on your mediator variable, but your mediator variable itself has a negative effect on your dependent variable. So those higher values on the mediator variable imply lower values on the dependent variable, or the other way around. Maybe your independent variable pushes down the values on your mediator variable, but that mediator variable actually has a positive effect on your dependent variable, so pushes up the values on your dependent variable. Yeah, so this is more an intuitive understanding about why that is the case. Yeah, but mathematically, it's obviously it's either A has to be negative or B has to be negative, but they can't both be negative, because that would imply that it's actually a positive indirect effect. Yeah, so that's a good thing to consider. Yeah, so either this is the case, X to Z is negative and Z to Y is positive, or this is the case, X to Z is positive, but Z to Y is negative. So if you have a simple relationship that's negative and that there should be an indirect mediation effect going on, then it has to be either one of those 2 situations. Now, so in general, the idea of this mediation is that you have some kind of initial effect from your independent variable to your dependent variable, and that initial effect can partially or completely be explained away by the effect of your independent variable on your mediator variable, and by implication by the effect that your mediator variable then has on your dependent variable. So the idea that mediation basically means that this initial effect that you have in the simple relationship, that this can be explained away, or at least partially be explained away, by the effect of X on Z and the effect that Z has on Y. Now, what does it mean? It means that the absolute value of the coefficient is larger when the model does not include your Z variable. Yeah, that's the idea, that the value of C apostrophe is smaller than the value of the C path. Yeah, absolute value. So basically meaning forgetting about the negative sign if there is one, just taking just the value without the negative or positive. So the absolute value of the coefficient should be larger when the mediator variable is not included. So when we're not adjusting or controlling for differences in the mediator, than when we are controlling for the mediator. Yeah, so that would indicate that the mediator is really explaining away part of that effect, yeah, or maybe even completely if you have complete mediation. there might also be another situation. It might actually be the case that the absolute value of your coefficient actually increases when you include your mediator or some z variable in the model. Yeah, that could happen. Yeah, it could be the case that you had maybe a positive coefficient to start out with in the simple relationship, and then you include a z variable in your model, and the coefficient became even more positive, an even larger positive number. Or you had a negative effect that you started out with in the simple relationship, and then you included a z variable, and it became even more negative, so even further removed from zero. And it could also be the case that the level of significance, so the associated p-value with your x variable changes. Maybe it could even be the case that you have an x variable that is not statistically significant in whatever way you deem you want to judge that. But once you include that third z variable, it does become statistically significant. Yeah, so that can actually happen. And it's useful to think about, well, what is going on then? It looks like mediation in that case. The only difference is that instead of the coefficient going down, so the absolute value of the coefficient going down, or the level of significance decreasing when you include that z variable, it's actually going up. Yeah, so significance, p-values go down, and absolute values of the coefficients actually go up. So we give this a different name. We don't call it mediation, because it doesn't really fit with having this kind of indirect effect like we have in a mediation model, but we call it suppression. Because the idea is that what we have here is that we have a direct effect of our x variable that is suppressed by a counteracting indirect effect. So in other words, the simple effect that we start out with before we take into account differences in that z variable, so that simple effect of x on y, this is actually an effect that is a suppressed version of the true direct effect of x on y, because it is being suppressed by this counteracting indirect effect. So the best way to understand it is to think about an example. So let's assume that I have an effect that I want to estimate. So for instance, I'm going to estimate the effect of number of cats that people have on how much they like statistics. And I find no significant effect. So I'm just going to put down the value 0. So maybe my regression coefficient is not very large and the p-value is super high. So I can't reject the null hypothesis that there is no effect. So I'm just going to keep assuming that it is a 0 effect because I don't know, I don't have any evidence that it's not so far. Yeah, and maybe then I re-estimate the model, but now I'm taking into account a third variable, for instance, how long people's hair is. Yeah, I don't know. I'm just making this stuff up as I go along, basically. Yeah, and now all of a sudden I find a significant effect of having cats on liking statistics. Well, what would have created this situation? Well, if the direct effect that we now find is a positive effect, and we didn't originally find it before we took into account differences in z, that means that there were probably two pathways from x to y. The direct positive effect that I now find for having cats on liking statistics, but also an indirect pathway that had to be negative, so that went into the other direction through length of hair. So then it could either be the situation that more hair makes people like cats more, but so it's correctly, no, having more cats makes people have longer hair, but longer hair actually decreases how much they like statistics, something like that. Yeah, so you would have to have an indirect effect that goes in the other direction than your direct effect, because then the original effect that you found would be a kind of average of those two effects, so they would just partially cancel out. Yeah, in the simple relationship. Yeah, so something like that would then be happening. So that's what we mean with suppression. If we have a direct effect that runs in the opposite direction than an indirect effect, so what you will then see happening is that only once you include once you include your z variable, then all of a sudden you find this direct effect for your x variable. Yeah, so this is called a situation where you have a suppressing relationship. Yeah, because not including z in your model basically suppresses the direct effect of x on y. Yeah. So that's one thing where it looks like mediation, but it's subtly different, because mediation implies that the direct and the indirect effect go in the same direction, whereas suppression implies that they go in different direction. One is positive and the other is negative. Now, we already discussed spurious relationships, and if you think back about how to draw conceptual models for spurious relationships, well, then what we are saying is, well, we have some kind of X variable which has some positive or maybe a negative effect on our dependent variable, and then there might be a third variable that is actually a cause of both our X variable and of our Y variable, so a confounding variable. Yeah, where we would say, well, if not including this variable in our model suggests that there is an effect of X and Y, but including the confounding variable suggests that there isn't an effect of X and Y, then this is called a spurious relationship. Yeah, spurious, basically just a fancy word for false, not true relationship. So we initially thought there was an effect of X and Y, but once we control for the Z variable, we actually don't find it anymore. So now we know that the effect of X and Y that we thought was due to the causal effect of X and Y actually is entirely due to the causal effect that Z had on X and Y. So entirely due to this third Z variable. Yeah, so this would be a situation where you have the original effect that you find disappear after you control for this confounding variable, which looks a lot, if you look at this, it looks a lot like the pictures that I used to describe mediation. Mediated relationships, right? So what is the difference between the two? Because they look incredibly similar, right? So what is the difference? Well, the difference is in how we theoretically think about the relationship between our X variable and our Z variable. Yeah. So what do we think is the relationship between our independent variable and that third Z variable? Yeah, and that really describes what the difference is between, on the one hand, mediation or suppression, and on the other hand, spuriousness. Because if we talk about mediation or suppression, then we assume that X is a cause of Z. Yeah, so in other words, we're saying the arrow runs from X to Z. Differences in how many cats people have lead to differences in how long their hair is. Yeah, and not the other way around. So in this case, if we talk about the mediating or suppressing relationship, we are treating the Z variable as an endogenous variable. Again, remember, what does endogenous mean? It means determined within the system of variable that we are considering. So in this case, we are saying that X is exogenous. There's no arrows running towards X, only away from it. But we have an arrow that runs from X to Z, indicating that as the Z variable that we're analyzing itself is partially or completely determined by this X variable. Yeah, so that's what would describe a mediating or a suppressing relationship. Whereas if we talk about spuriousness, we assume that the arrow actually runs from Z to X rather than from X to Z. Yeah, so in that case, we say, well, no, our X variable is exogenous because there's actually an arrow running from Z to X. Yeah, so that's the difference between these two things. Yeah, remember back that when we discussed about the assumptions that we needed to have fulfilled if we want to talk about X having a causal effect, that this assumption can be described as the assumption of exogeneity, that X is actually an exogenous variable as we have in this situation rather than an endogenous variable such as we have in this situation. Because in this situation, we would need to include this Z variable in our model, because otherwise we might get a spurious effect. So think that there really is a causal effect, while actually there is none. Yeah, so this is basically how to distinguish between these different situations. So the difference is really in do you think that the arrow runs from X to Z? So do you think that X has a causal effect on Z, or do you think that Z has a causal effect on X? Which also means that if you think about what are relevant control variables, if you want to make stronger causal inferences, that if you can assume this to be the case, yeah, that Z has an effect on X, Yeah, and again, you will need to base that on theoretical reasoning because you can't ever prove that something has a causal effect. But if you assume that this is the case and you can measure z, then obviously you should include z as a control variable, because obviously then it can be a confounding variable. However, this situation, if it's actually the other way around, is a little bit more complicated, because then it really depends on your theoretical causal mechanism. Yeah, so if you say, well, z is a variable where x has an indirect effect on y via z, but z is not actually something that my theory predicts, this indirect effect, so it's not actually part of the causal mechanism, then you might want to control for differences in z, because then basically z can be a confounder, because otherwise you find a relationship between x and y that might look like it's consistent with your causal mechanism, but actually it isn't, because it runs through a different pathway than the one that you are theorizing. Yeah, so in that case, it makes sense to include z as a confounding variable. However, of course, usually if you have a mediation hypothesis, you say, no, actually z is actually part of exactly the causal mechanism that I hypothesize about. So that's actually exactly why I affect x to have an effect on y. And so this is something to be careful about, because I often see this happening, not just with student papers, but sometimes also with published papers, is that people include variables as control variables that are actually part of the causal mechanisms that they are trying to test. And that can lead to super misleading results, because imagine a situation of perfect mediation. Yeah, so that z is a perfect mediator variable. And it's also the mediator variable, or one of the mediator variables, that is completely consistent with your causal mechanism. So if you're not careful, you might be in a situation where you say, I'm going to test my causal mechanism by estimating the effect of x and y. And I'm going to include the z variable as a potential as a control variable because it's a potential confounder. And then you look at your results and you find no effect of x on y. And you say, well, that means that my hypothesis is not supported. I don't find the effect empirically that I expected under the causal mechanism. Where, as a matter of fact, it might be the case that the reason you're not finding the effect of x on y is because you're controlling for the z variable, which is exactly the reason why x has an effect on y. So in that case, you are over-controlling your regression model. So you're controlling for too much, because z is actually exactly the reason why you expect this relationship to be there in the first place. Yeah, so this is really something that you should be aware of at some point, that what is a confounding variable is always also dependent on, well, what is your theory? What are exactly the causal mechanisms that you're trying to test? And do these variables, what relationships do these variables have with the variables that you're trying to test, and the mechanisms for why you're expecting these variables to have an effect? Yeah, so that's an important one to remember, because I see this go wrong quite a bit. Yeah, so that's a bit more at the conceptual level. That was it for me for this B lecture. I'll hope to see you on one of the Zoom meetings. Bye bye, ciao ciao, and take care of yourself.